Okay, so do you remember in rollover we talked about the use of the second derivative and what this can tell us? Because my plan is not to go over this again. You didn't do this with me, but you did this with Miss Chalmers. You did this with Miss Chalmers. Okay, so I'll talk to you about it now then. I'll talk to you about it now, okay? Now, normally, the first derivative tells us whether the curve is going upwards or whether the curve is going downwards or whether the curve is flat, okay? That's what the first derivative tells us. If the first derivative is less than 0, what kind of shape of the graph does it mean that we have? It means it's going down, and we would call, if the first derivative was less than 0, we would say that it is a decreasing function. And obviously, if it is greater than 0, then we would say that it is an increasing function, okay? The second derivative tells us something about the shape of the graph, okay? So we're going to read through these sort of sections that we've got here, and this should hopefully refresh some of the things that you would have looked at with Miss Chalmers way back in rollover. Now, this beginning part, we're talking about the shape of a graph is concave if it makes this kind of shape, okay? The way that I remember that this kind of upward sort of N shape is concave is I literally think of this diagram and I think it looks a bit like a cave where there'd be a little entrance to the cave and there'd be a kind of a little pathway to get into the cave. That's how I remember that one is concave. And when we look at the information under here, it says the gradient is always decreasing. So if you look here, to begin with, it has quite a big positive gradient. The gradient is still positive over here, but it's less positive. And when it gets to the top, the gradient is 0. And then the gradient is becoming negative, and then it's actually becoming a bit more negative over here. So the gradient is becoming more negative. In other words, the change of the gradient is negative. The change of the gradient is the second derivative. So if the change of the gradient is negative, in other words, the gradient is also decreasing, you get this concave shape. So it says here, f of x is concave when the second derivative is less than or equal to 0. Some definitions say less than 0, some definitions say less than or equal to. Edexcel have said they don't mind which definition that you use here. They don't mind if you're using either of them. We'll come out of this middle bit, we're going to have a look at the convex bit. The convex, I then think, it's got that kind of V sort of shape to it, and convex, I think, sounds like the V is quite strong in that. Although concave has got a V, I think of it as concave, like the k noise, whereas it's convex. That makes me very much think of this bit as being to do with convex, okay? If you look at this bit, the gradient is negative, then it goes to 0, then it's slightly positive, and then it becomes sort of more positive over in this area. So for this section, the gradient is going from a negative to slightly to 0 to slightly positive to quite steep and positive, which means that the gradient is changing and increasing. In other words, it means that the rate of change of the gradient is positive, or it could be equal to 0 in that area. So if you have a curve and the second derivative is greater than 0, then we would say that it is convex, and you can see that that bit's written down there as well. Another way of thinking about this concave section is that the curve is swerving to the right. It's kind of it's like if you were in a car, it's like it's turning to the right-hand side. And in a convex sort of situation, if you were in a car, it's like the car is turning to the left, okay? The point that's in the middle here, the point of inflection, is where it is neither swerving to the left or the right. It's where it's just about to change. From here, it is swerving to the right, and then at that point, it changes and it begins to swerve to the left. Just imagine that for a second, that this was like a bird's eye view and you were driving in a car along this line. This whole way where it's concave, making that curved shape, you're swerving with the steering wheel to the right. when you're going in this point here, what can you say about your steering wheel? It's back in the center again, and please don't be doing driving like this. I know some of you are doing like driving lessons. Don't do like crazy driving like this. And then you're starting to turn the wheel back to the left again. So the point of inflection is this bit here where the gradient itself is not changing. So the gradient of the gradient is 0. It's getting a bit weird. It's getting a bit like the gradient of the gradient. You could talk about the gradient of the gradient of the gradient if you wanted to, but we're going to not do that at all. And it says, note that points of inflection, as with this example, are not necessarily stationary points. What does that mean? Point of inflection is not necessarily a stationary point. What's a stationary point? When the gradient is 0. So here, the second derivative is 0, but we can see that the first derivative is not 0 in this particular example. There may be cases where the gradient is 0 and the second derivative is 0. So if I was going to draw a quick example of what that might look like, I'll squeeze it in down here. It could be something that was like this. So it's swerving to the right, it's neither swerving to the right nor the left, and then it's swerving to the left. And this point in the middle is the point of inflection. It happens also that it's a stationary point because it's got a 0 gradient. So we're just adding in a couple of other definitions basically. The new definitions that we're adding in is if the second derivative is less than 0, then we say that it is concave. If the second derivative is greater than 0, then we say that it is convex. If the second derivative is equal to 0, we say that it is a point of inflection. Okay? This is year 12. These 3 bits is year 13. They can ask you about either of them when you have your exam. If they ask you to say that a function is increasing, you would use the first derivative. If they ask you to say when a function is concave, you use the second derivative. So it's just adding in a couple of new things that we've got there. Another way that you might like to remember these things, that it's less than 0, is to do with this point at the top here. What would we normally describe this point as at the top? A stationary point? And can you be more specific about what type of stationary point it is? A turning point? What type of turning point? It's a maximum. What do you know for maximum points? Good. The second derivative is less than 0 for a maximum. So that's another way of remembering that concave, that kind of shape, is less than 0 because the gradient is decreasing. This point, which is a minimum, we know that the second derivative at a turning point is greater than 0 for a minimum point, hence it being the second derivative is greater than 0 when it's convex. So just to reiterate that point one final time, we're not talking about this one point here when we're talking about concave. When we are talking about something being concave, we are talking about that entire section. When we're talking about something being convex, we're not talking about just the minimum point, we're talking about that one whole section that we've got there, which is convex. Okay? Does this ring some bells with what you did in rollover? But is it okay that we've gone over it again? It's not a waste of time, because I'm happy to move on if you want. Should we move on? Okay, so I'm not going to do these examples that we've got here, because I think you know what you'd need to do. You would just need to differentiate them twice, and then show whether it's greater than 0 or less than 0. Same here, you need to just differentiate it twice. This one, you need to differentiate it twice and make it equal to 0 because it's talking about a point of inflection. Okay? Just good to have that as a recap, and at least we've then got it on a video if you need to see how that's explained. So, we are now going to hopefully squeeze this in before the end of the lesson. This is the last bit of differentiation, and there's nothing really new here. All you need to do is connect together all of the different things that we've done so far. And I think that you should be, I think you should actually quite enjoy this topic. I quite like this one. So the topic is called connected rates of change. Sometimes it's called relating rates of change. Rates of change is talking about gradients. And these are the questions, if you've had a look right at the beginning of this topic, I remember I made you look at these questions and you were like, oh, these kind of remind me of some of the year 12 style differentiation, like the kind of worded problems. And that's what we're going to have a look at for this type of problem. The best way to teach this topic is for me to dive straight in with an example. So let's just read what's happening here. It says, determine the rate of change of the area A of a circle when the radius r is 3 centimetres, given that the radius is changing at a rate of 5 centimetres per second. That all sounds very, very abstract, so let's try and break down what's actually happening here. We're talking about a circle whose radius is changing at a rate of 5 centimetres per second. Just think for a moment, what is actually happening to that circle? What would that circle look like if its radius is changing at a rate of 5 centimetres per second? I've just seen Hamza going with his arms, like making like a bigger circle, which is exactly what's happening. We've got a circle that's radius. In fact, I could probably like put an example of this on the board to show you it done nicely. We've got a circle that every second it is like increasing at a constant rate, like that. The radius is going 5 centimetres bigger every second. And then what it wants us to do is to think about how the area is changing. Now, do you expect the area to be changing at the same rate as the radius is changing? So we've got some yeses and some nos. Who thinks they can try and justify their yes or their no? Pardon? The rate might be greater, the rate might be smaller. I don't think they're going to be the same. Definitely not going to be the same. Why would they not be the same? Because one's proportional to r squared and the radius is increasing at a constant rate. So if the radius is increasing at a constant rate, the area can't be increasing at a constant rate because it's proportional to r squared. So let's see how this is actually going to behave. Right, we're going to break the question down and we're going to think about how we can represent lots of the worded parts of the questions, how we can translate them into mathematical kinds of terms. So the first thing says the rate of change of the area. And there's a tip over here. Whenever you see the word rate, think of with respect to time. Because rate, if you talk about the rate of something, it's like how quickly something is happening or how much it's happening in a given amount of time. So what do we think the rate of change of the area would be? How would we express that using a piece of... pardon? It would not be 5t plus 3. There's going to be something to do with this dt. It's going to be something dt. dA, because we're talking about how the area is changing with respect to time. Remember, dy by dx is saying how does y change with respect to x. This is saying how is the area going to change with respect to time. In other words, what is the rate of change of area? Remember, rate means how something is changing with respect to time. If I said someone is working at a very quick rate, it means that they are doing a lot of work in a certain amount of time. If someone is working at a slow rate, I'm not going to look at any particular people, it means that they would be doing not much work in the same amount of time. So it's always out of the same amount of time there. Then we've got the rate of change of the radius is 5. Again, we've got rate in here. So what do you think the rate of change of the radius is 5? dr dt is 5? How do I say is 5? Equals 5, not difficult. Equals 5. And then we've also got something in this question where it's talking about the area of a circle. How can I say what the area of a circle is? Please tell me you remember this. No. Say what is the area of a circle? Is just pi r squared. Okay, so we're not going to do the 9 pi, but I know where you were going for with that. So we've got these 3 different pieces of information. The thing that we are trying to find out is the rate of change of the area. This is the thing that we want to find out, okay? We're trying to find out what dA dt is. We know what dr dt is. We know what dr dt is that we've got here. Now this is the trick that you're going to do to connect rates of change together. Another way of working out what dA dt is to split it into dA by d something and d something by dt. Because the dr, if I put dr in here and dr in here, can you see how the left-hand side and the right-hand side are equivalent? Because the drs are kind of cancelling out in the same way that it does with the chain rule. So these things being multiplied by together, this is the thing we want. We don't have dA by dr, and we do have dr by dt. Okay, so this is dA dr. This is differentiating a with respect to r. How could I find dA by dr? Luke? I could use the area of the circle. If I differentiate both sides here with respect to r, a differentiated with respect to r is dA dr, which is 2 pi r. Interesting, isn't it? The area of a circle, when you differentiate it, you get, which is the circumference. Okay. So I want to find out what dA by dt is. dA by dt is dA by dr, which is 2 pi r, multiplied by dr by dt. Now they told us that dr by dt was 5, so it is 10 pi r. So we're nearly there. What's the last thing that you think we should be able to do for this question? Because we haven't quite come up with what the dA by dt is yet. We haven't come up with the rate of change. Good, it says when r equals 3. So we know that r is equal to 3. So dA by dt is equal to 10 pi times 3, which is 30 pi. So the rate of change of the area when the radius is 3 is 30 pi. What would the units be for that? The rate of change of the area. Good. Centimetres squared. Per second, you do s with the -1, because obviously to the -1 would be like per second or like over seconds. So that would be our answer for this one. You may write that in a calculator and actually get it as a numerical value. Depends on the context of the question. I'm interested in this last thing we talked about here, where we talked about the units, where we got centimetres squared per second. Look how that would be, a at the top would be centimetres squared, and the time on the bottom is seconds. So what do we think the rate of change of the radius is? What's the units? Yeah, and look, there it is there. Centimetres s minus 1. And the rate of change of the area we just talked about is centimetres squared per second. What would the units of dA by dr be? Just centimetres. Yeah, because you've got centimetres squared divided by centimetres, so the unit would be centimetres, but we don't really need that. The units that you get given in the question are often a really, really big clue about how to do that. Okay? So I'll give you a bit of time to write that one up. Yes?
Can you go through how you got dA over dr?
Yeah, this how we got this bit, or how we set this bit up.
How do you go from that bit to the bit above it?
So here I literally differentiated this with respect to r, and I differentiated this with respect to r. Because if you imagine differentiating r squared becomes 2r, and so you've just got the pi there as well. Okay. This bit that we did here, I'm just going to erase this and do it one more time. The way that you do this beginning bit is you write down the thing that you are looking for, which is dA by dt, and you split it out. So you write a dA without something, and you write the dt. You have the bit you want at the beginning, at the top, the bit you want at the end down here, and then you think, okay, well, what's the only other option of things I can fill in? The only other variable that we have here is dr, so dr goes in both of them. That's how you set up this thing that you've got here. You split it out, you connect those rates of change together. So after you've got that one written down, I will leave it on this page. I'd like you to have a go at getting started on this one, and then we'll go through it together in just a moment. Okay?